Welcome back, friends. Welcome to another video tutorial from Shramu's Biology. In this video tutorial, we'll be talking about gas chromatography. Gas chromatography is a technique of separating different chemical compounds based on their volatility, using gas as a mobile phase. Now, there are a lot more terms that I talked in this last sentence, but what those things are? In any kind of chromatography, we generally intend to separate different molecules from each other, from a mixture of other molecules. So let's say we are talking about an organic solvent or organic molecule of our interest, and we have a mixture of that molecules together. We want to separate them based on some of their properties, and which property we are using here to separate is the volatility and their polarity. There are these two features that we use to separate molecules using gas chromatography. Now, in any sort of chromatography you are going to study in your life, remember three things to know about each and every chromatography. First thing is, what are their stationary and mobile phase? So let me write it these things first, then I'll explain all these things and what this stands for. First thing that you should always remember is what is the mobile phase and what is the stationary phase. That is, you need to know. That's the first thing you need to know. The second thing is, what are the feature or characteristics that you use to separate those compounds. And third thing is the mechanism by which you separate those molecules from each other. So once you know these three things about any chromatography technique, whether it's a gas chromatography or liquid chromatography or column chromatography, once you know these three things, you know that feature very well. So now let's begin with the process of gas chromatography. This is called gas chromatography because gas is taken as a mobile phase for this chromatography. Gas is used as a carrier for this chromatography. That's why we call it gas chromatography, because the mobile phase is called the gas carrier. And the example of the gas that acts as a carrier of all those chemical molecules that we want to separate, normally the gas is inert gas. An example of such inert gas is helium. Mostly we use helium as a carrier gas molecule that will bring all those solutes and separate those solutes and pass those solutes through the stationary phase of this column. Now, in any chromatography, there is a specific region called column where all the separation mechanism take place. Okay. Now, there are different instrument portions like the start point and the detector and everything. That's a huge range of instrumentation. But there is a major instrument where the actual mechanism of separation take place. That is known as the column. Okay. It's known as column. And the column that we use in gas chromatography, that column is filled with stationary phase. Remember this. The column contains the stationary phase. Now, the stationary phase is always stagnant. It's placed in an area. It is not moving. While the mobile phase, as the name suggests, is moving. So, the gas acting as a mobile phase, the inert gas, it's moving and it's taking the solutes with it, while the stationary phase is fixed in the column. So now the idea is this gas will move through the stationary phase which is present in the column, and there will be interaction of this gas containing all the chemical molecules along with the stationary phase, and this interaction will help these molecules to be properly separated from each other. That is the idea. And what exact mechanism they follow to separate, that we will talk about right after a few minutes. So here we use gas chromatography to separate mostly organic compounds that range the molecular weight of like less than 500 or less than 800, mostly in between the 200 to 800 molecular weight, Dalton molecular weight. Okay. Otherwise, normally, and we mostly use the organic compounds to separate, but also we can use inorganic compounds. But the one most important thing and the feature which we use to separate using gas chromatography, that is the characteristic. Remember, this is two things. One is the volatility and second thing is the polarity. So all the compounds that we will separate using gas chromatography will be based on their volatility and polarity. So for separating chemical compounds using gas chromatography, that molecule must be volatile. Otherwise, we cannot separate those molecules using gas chromatography. So you have to have a volatile compound in the gas chromatography running. And the volatile compound that we will talk here, that means if you heat this compound, it will get the vapor content of that molecule, and that vapor will be carried through this column with the help of this inert helium gas or any other sort of gas that we use as a mobile phase, and then the detection will be done. So this is the prime feature that we are looking here. So in that case, if you are thinking like throwing a stone and separating different types of stone or sand chips and stuff, it won't be possible because you cannot flame them to vapor. We need something that we can flame into vapor. So we need to heat them to form vapor, and then the whole process will run. So now as you know the basics of the gas chromatography, that what it is required and why we are doing gas chromatography, now we can focus on the instrumentation of gas chromatography and overall idea about the gas chromatography. Once we get that idea, then we will dig deep into the mechanism of the separation using gas chromatography. Okay, so let's begin with the instrumentation and how the gas chromatography thing arranged. It starts with like here, this is the mobile phase thing, that is the inert gas chamber. This is the mobile phase through which the inert gas will be passed, and in between this is the chamber, the column. Actually it starts from here. Actually inert gas is going on, and there is a specific point there in between, which is the sample injection point. Okay, this is the sample injection point, and then we have the rest of the column. Let's say it's just a simple spiral. It's here, and at the end of this column there will be like the detector. This is the detector. Okay, and this detector is attached to some computer, which will give us some idea about the graphs and stuff that we'll be talking about later. But this is a very simple, very simple overview of how the gas chromatography instrumentation look like. It starts with the firing portion with the mobile phase, where we have all those inert gases that we can use here. The gas will start to move from this area. There is a point known as the switch or the sample entry point. The sample entry switch, we can tell this is the one, and the rest of the column where the separation will take place. And ultimately we have the detector, which will detect the presence of different compounds, which will reach first or second. So I can give a simple analogy to remember this. Just think of all this gas chromatography or liquid chromatography, whatever you are studying, as there are few people involved in a run. So we have a race going on. From this is the start, this is the end. We have a racing. Everyone is at the same time, same line, they present here. At the same time, all of them are present in the same line. Now what will happen? All of them suddenly start, whenever there is a firing, they'll start racing. The same thing, the sample, whenever we put the sample, they start the racing. And as they start racing, they will go through this whole area, and ultimately this is the finish line. Now the thing is, it depends on during the racing. If you run fast, you'll reach fast. If you run slow, you'll reach later. That is the same thing here in this case. Now the way those molecules interact with this stationary phase will ultimately dictates which molecule will come first, which molecule will come last. That is the way. So they will start together, but at the end the detector will receive one of the compound at a time, and the time duration taken for each of those molecules, each of those compounds to reach is very important, because that is the thing that actually helps the detector to identify which compound is moving. So as we are separating compounds, like we can easily pick that this is the compound comes first, B comes second, C comes third. So now we know all the components that are present in this mixture. because at the very beginning we don't have any idea about that, right? So the time taken for all those compounds to reach one at a time, each of those time taken is known as the retention time for all those chemical compounds. And this retention time is the feature that actually help us to figure out the number of different compounds present in the mixture. Okay, so now let's begin with this idea. Mobile phase, it contains all those gases, mostly inert gases is most of the time, like helium, but it may also carry in some cases nitrogen or hydrogen gas. It depends on the different type of column that we use. So there are two types of column that we can find here. It could be packed bed column or it could be capillary column. Now normally, as I told you, in the stationary phase and mobile phase, the mobile phase is gas here, inert gas, but the stationary phase is liquid or solid. It could be liquid or solid. So in this case we are talking about, let's say, packed bed column, and you are looking at also at a solid also as a liquid stationary phase. But the liquid that is present in the stationary phase will be high volatile compound. That will also be something which is high boiling liquid. That's not volatile, sorry, it's high boiling liquid that should be present here. So now the situation is gas is moving one at a time here. Now there are different systems present here which will help the gas to flow in a specific thin line instead of a gathered one. Now this is very interesting area because this is a sampling port and sampling switch where we actually inject the sample that we want to separate. Okay, so inject the sample here. Now this is the knob or switch which is heated in huge temperatures, because this is where whenever we inject the sample it gets heated. Now it starts to produce a vapor of that compound. So once the vapors are produced here, it will be mixed with this tube, and then the inert gas carry that vapor through the place. Now first few region of this tube is not called the stationary phase. Stationary phase begins after some area, after this injection of the sample, and rest of the part will be the stationary phase area which I draw here. This is the start point of stationary phase, this is the end point of the stationary phase. So now what I told you is the sample is injected there, it's heated there. So let me write it here. So we have a heated, ultimately it forms vapor. Once the vapor is formed, it is being migrated through that area. Now let's say it is not only having this same compound. Let's say we are talking about three different compounds, one red, one black, and let's say one green. I don't know whether you can see the green because it's very faint color here, but I'll be drawing in little mix. So there's a mixture of three chemical compounds that we wanted to separate. So we inject that sample here at the very beginning. This is the place of the sample where we put all those things like black, green and red here. Now once they're injected, now they are being transported through this stationary phase. Now they will interact with the stationary phase, and this interaction with the stationary phase is the actual mechanism that will help them to be separated. Ultimately that can be detected by the detector. So now what actually happens here in this area? So let me zoom into it a little bit. Let me zoom in this area. Let's say this is the tube. This is the stationary phase, a portion of stationary phase I zoom in. Okay. Now in the stationary phase, as I told you, we have all those liquid ingredients. Let's say this is the different liquid stationary phase that are packed bed. As I told you, packed bed means it's filled with so many other components inside. So this is the packed bed column, and now we have the mixture of three molecules. We have this black, we have the red, and we have the green, for example. Okay, so we have this three type of molecules present there, and they will start moving by this pressure. Now remember, it's not only like we are injecting the sample, but we also need to create a pressure so that all these things are moving in the right direction, and the direction in this case is towards the detector. So for that we need to apply some pressure. So we have some sort of pressure creating or a pump like thing that is present here, which will pressure or force the rest of the flow to move towards the detector. Okay, and that is a part of the instrumentation. Now here is the most important point where we'll see the mechanism of separation. As I told you, the mechanism of separation in case of gas chromatography is based on volatility and polarity of those compounds. Now we have drawn three different compounds, three different molecules here. This green, blue and red, green, black and red. Now let's say they have different features. Let's say this black is most volatile, okay, and polar. For example, it's most volatile and non-polar, for example. Now let's say green is a polar and moderately volatile. And third one is the red is volatile and polar. So what will happen in this case? Volatile and polar, these are the two characteristics that we use to separate them, right? So now what actually happens in this column? You know, let's say this column that we make, this column is of polar. It's made with polar liquid, because I told you it's a liquid phase stationary, so liquid stationary phase. So it is a polar molecule that is making the stationary phase. And all those molecules, the mixture is moving. Now remember one thing, if there is a polar molecule in the stationary phase and this other molecules, the mobile phase molecule, constantly interact with those stationary phase molecules. So if the compound is polar, the interaction between polar and polar will be more. So the polar molecules tend to interact towards the polar stationary phase. So they will take more time to reach the end. But if there is any non-polar molecules in this mixture, that will never interact with the polar molecule, because non-polar molecules don't like hydrophilicity, right? So they don't need polar molecules. They start to fly very, very fast. So any non-polar molecule will reach very fast if the stationary phase is polar, remember. But if the stationary phase is non-polar, then polar molecules will reach fast. Get the idea? The second thing is about the volatility. Any compound with very high volatility will reach the detector first. So the more the volatility, the faster those molecules will move. So the faster they will reach the detector. So the retention time is very less. But those who have the same type of nature of polarity with the stationary phase will move slow. Those molecules have opposite of the polarity of the stationary phase will move fast. So based on these two important mechanisms, what we can tell is that these molecules are constantly interacting with these stationary phase molecules. While they are interacting, they have different features. Those features will help them to be separated. How? Let's say here, black is the most volatile. So they will try to fly very, very fast. Now look at the feature of their polarity. They are non-polar, but we are using a polar stationary phase. So this black one will run very, very fast ahead of everything in this column, and it will come out fast. So black will come at the very first point in the detector. So the black will be detected in the very first point by the detector at the end. Now second is between red and green. Green is polar, but it is moderately volatile. While red is also polar, but it is highly volatile. So as red contains more volatility compared with the green, red will go after the black and green will go after the red, because it has less volatility. Though both of them are polar, so they tends to interact with this polar liquid stationary phase a little bit in the middle. So they will take some time compared with the black one, but they will reach eventually afterwards. So first black will be separated, then the red, then the green. Okay, so whenever the detector detects the outcome of all those different chemical compounds, it provides that as a signal. and that signal is recorded, and once it's fed into the computer converts the signal to plot a graph with the signal, and that graph is going to tell us about how exactly that whole process takes place. So let me erase some part of it and explain this graph. Most probably I'll do the graph explanation here. So let's explain the graph here. So what we will have a time in the x-axis. In the y-axis we have the signal, remember. So what we are receiving in the very beginning, at the very first, black is transmitted out. Now the concentration of this black, if the concentration is high, it does not matter about the concentration whether the black will reach or first or second. This time taken will be required on the characteristics, the volatility and the polarity. But if black have higher concentration, more blacks will be hitting the detector at the very beginning, so the peak height will be more. So let's say here at the very beginning it starts with that, and the signal is very high for the black. Now let's say it comes red. Red contains the highest concentration. After some time red start to come out, but the concentration of the red will be further, and then finally green is, the concentration of green is also very low and its retention time is also less, so we'll see the green at the end. So this is the type of peak that we will see. So now if we look at this peak, it's going to tell us very important insights. It is going to tell us that black is eluted very first, then red, then green. This is the first observation. Second thing, that the area that is plotted by the graph, this is the whole thing about, this is called the area or the peak area. This peak area is directly proportional with the concentration of that chemical compound in the mixture. Here you can see easily that the red compound concentration is much higher than the black as well as than the green. Okay, and it also is corresponding with the peak height, so you can measure either peak height or peak area to get an idea about the concentration of that chemical compound in the mixture. But mostly we rely on the area, the peak area, to actually find out the concentration. So that in a sense is how we get, by looking at the graph, we can tell whichever compounds are present in the mixture. That is the idea of gas chromatography in our sense, that we separate them based on volatility and polarity. Now if you look at this column usually ranges from 3 foot to 6 foot. Sometimes it gets like 8 to 12 foot long, but very rarely. Now the design of the column and which material will be present as the stationary phase will vary based on the type of chemical compound we want to separate. Okay, rest of the thing, the mechanism remains the same. It's the simple mechanism but slightly twist for different types of solutes to be separated. Mostly used for chemistry like organic or inorganic, but mostly organic compounds separated much well with the gas chromatography. And the advantages of this gas chromatography is very fast, it's very sensitive. That means you get a very high quality of quantitative data with this. And it's also like very sensitive, means it can easily detect very low amount of chemical compounds, even in the picogram level of compounds, that is parts per billion concentration of the compound can be detected with using gas chromatography. That's an added advantage. Though you need some sort of technicians to handle this whole process, you need to have an understanding of this process to analyze the graphs and data, but still it is a very fast, reliable and detectable way of separating compounds. So use it very often there. Now nowadays we not only use this graph to analyze and find out the number of chemical compounds present in the sample, we tag this gas chromatography with mass spectrometry and convert them, which is called as gas chromatography mass spectrometry or GCMS. This is a new modern approach of tagging mass spectrometry with the gas chromatography so that we can get a confirmed idea about what chemical compounds we are dealing with. That's a very added advantage that we have now in modern times. Earlier we simply rely on the graph, but now mass spectrometry is another technique which will help us to identify exact chemical structures. If you want to know about mass spectrometry, you can watch the complete video series about mass spectrometry that is present in my channel. You can just search that name, or I'll put that link in the description to watch. Now the disadvantage of gas chromatography is that for using gas chromatography, you can only use those compounds which are volatile, which can be converted into vapor. You cannot use any other compound of your interest that should be volatile to use them in gas chromatography. That is the only disadvantage. And second thing, if you are using some dirty samples or the complicated samples like urine, in that case those things sometimes can clog this column, and there are some issues can be possible. So to beat those problems, we need to have a cleaning step before running them in the column. That is another kind of disadvantage, but mostly it's very advantageous technique to use in separation of organic chemical compounds. So that in a sense is the gas chromatography. I hope you understand this video. If you like this video, please hit the like button, subscribe to my channel to get more videos like that, share this video with your friends. Thank you.